Factor theorem and remainder theorem. In the last section, we limited ourselves to finding the intercepts or zeros of polynomials that factored simply, or we turned to technology. In this section, we will look at algebraic techniques for finding the zeros of polynomials like h of t equals t cubed plus 4t squared plus t minus 6. Long division. In the last section, we saw that we could write a polynomial as a product of factors, each corresponding to a horizontal intercept. If we knew that x equals 2 was an intercept of the polynomial x cubed plus 4x squared minus 5x minus 14, we might guess that the polynomial could be factored as x cubed plus 4x squared minus 5x minus 14 equals x minus 2 multiplied by something. To find that something, we can use the polynomial division. Example 1. Divide x cubed plus 4x squared minus 5x minus 14 by x minus 2. Start by writing the problem out in long division form. Now we divide the leading terms. X cubed divided by x equals x squared. It is best to align it above the same power term in the dividend. Now multiply that x squared by x minus 2 and write the result below the dividend. Now subtract that expression from the dividend. Again, divide the leading term of the remainder by the leading term of the divisor. 6x squared divided by x equals 6x. We add this to the result, multiplying 6x by x minus 2 and subtract. Repeat the process one last time. This tells us that x cubed plus 4x squared minus 5x minus 14 divided by x minus 2 is x squared plus 6x plus 7 with a remainder of 0. This also means that we can factor x cubed plus 4x squared minus 5x minus 14 as x minus 2 multiplied by x squared plus 6x plus 7. This gives us a way to find the intercepts of this polynomial. Example 2. Find the horizontal intercepts of h of x equals x cubed plus 4x squared minus 5x minus 14. To find the horizontal intercepts, we need to solve h of x equals 0. From the previous example, we know the function can be factored as h of x equals x minus 2 multiplied by x squared plus 6x plus 7. H of x equals x minus 2 multiplied by x squared plus 6x plus 7 equals 0 when x equals 2 or when x squared plus 6x plus 7 equals 0. This doesn't factor nicely, but we could use the quadratic formula to find the remaining two zeros. X equals negative 6 plus or minus square root of 6 squared minus 4 multiplied by 1 multiplied by 7 divided by 2 multiplied by 1 equals negative 3 plus or minus the square root of 2. The horizontal intercepts will be at 2, 0, negative 3 minus square root of 2, 0, and negative 3 plus square root of 2, 0. Try it now. Divide 2x cubed minus 7x plus 3 by x plus 3 using long division. The factor and remainder theorems. When we divide a polynomial p of x by some divisor, polynomial d of x, we will get a quotient polynomial q of x and possibly a remainder r of x. In other words, p of x equals d of x multiplied by q of x plus r of x. Because of the division, the remainder will either be 0 or a polynomial of lower degree than d of x. Because of this, if we divide a polynomial by a term of the form x minus c, then the remainder will be 0 or a constant. If p of x equals x minus c multiplied by q of x plus r, then p of c equals c minus c multiplied by q of c plus r equals 0 plus r equals r, which establishes the remainder theorem. The remainder theorem. If p of x is a polynomial of degree 1 or greater and c is a real number, then when p of x is divided by x minus c, the remainder is p of c. If x minus c is a factor of the polynomial p, then p of x equals x minus c multiplied by q of x for some polynomial q. Then p of c equals c minus c multiplied by q of c equals 0, showing c is a 0 of the polynomial. This shouldn't surprise us. We already knew that if the polynomial factors, it reveals the roots. If p of c equals 0, then the remainder theorem tells us that if p is divided by x minus c, then the remainder will be 0, which means x minus c is a factor of p. The factor theorem. If p of x is a non-zero polynomial, then the real number c is a 0 of p of x if and only if x minus c is a factor of p of x. Synthetic division. Since dividing by x minus c is a way to check if a number is a 0 of the polynomial, it would be nice to have a faster way to divide by x minus c than having to use long division every time. Happily, quicker ways have been discovered. Let's look back at the long division we did in example 1 and try to streamline it. First, let's change all the subtractions into additions by distributing through the negatives. Next, observe that the terms negative x cubed, negative 6x squared, and negative 7x are the exact opposite of the terms above them. The algorithm we use ensures this is always the case, so we can omit them without losing any information. Also note that the terms we bring down, namely the negative 5x and negative 14, aren't really necessary to recopy, so we omit them too. Now, let's move things up a bit, and for reasons which will become clear in a moment, copy the x cubed into the last row. Note that by arranging things in this manner, each term in the last row is obtained by adding the two terms above it. Notice also that the quotient polynomial can be obtained by dividing each of the first three terms in the last row by x and adding the results. If you take the time to work back through the original division problem, you will find that this is exactly the way we determine the quotient polynomial. This means that we no longer need to write the quotient polynomial down, nor the x in the divisor, to determine our answer. We've streamlined things quite a bit so far, but we can still do more. Let's take a moment to remind ourselves that 2x squared, 12x, and 14 came from in the second row. Each of these terms was obtained by multiplying the terms in the quotient x squared, 6x, and 7, respectively, by the negative 2 and x minus 2, then by negative 1, when we change the subtraction to addition. Multiplying by negative 2, then by negative 1 is the same as multiplying by 2, so we replace the negative 2 in the divisor by 2. Furthermore, the coefficients of the quotient polynomial match the coefficients of the first three terms in the last row, so we now take the plunge and write only the coefficients of the terms to get. We have constructed a synthetic division table for this polynomial division problem. Let's rework our division problem using the table to see how it streamlines the division process. To divide x cubed plus 4x squared minus 5x minus 14 by x minus 2, we write 2 in the place of the divisor and the coefficients of x cubed plus 4x squared minus 5x minus 14 in for the dividend. Then bring down the first coefficient of the dividend. Next, take the 2 from the divisor and multiply by the 1 that was brought down to get 2. Write this underneath the 4, then add to get 6. Now take the 2 from the divisor times the 6 to get 12 and add it to the negative 5 to get 7. Finally, take the 2 in the divisor times the 7 to get 14, add it to the negative 14 to get 0. The first three numbers in the last row of our table are the coefficients of the quotient polynomial. Remember, we started with a third degree polynomial and divided by a first degree polynomial, so the quotient is a second degree polynomial. Hence, the quotient is x squared plus 6x plus 7. The number in the box is the remainder. Synthetic division is our tool of choice for dividing polynomials by divisors of the form x minus c. It is important to note that it works only for these kinds of divisors. Also take note that when a polynomial of degree at least 1 is divided by x minus c, the result will be a polynomial of exactly 1 less degree. Finally, it is worth the time to trace each step in synthetic division back to its corresponding step in long division.